Thanks for coming. How many people have been to a meetup before this meetup? Yeah, everyone. Okay, some new people here. Good. So this is our third meetup. The first one we kind of just went over installing tools. So we'll help whoever doesn't have the tools install. We'll help that, so you can kind of catch up. And then the second meetup we kind of did the first meetup we flashed a LED. And then the second meetup we flashed an infrared LED to control a TV. So we just flashed it faster in a certain way. And this meetup, we're going to flash LEDs that are all connected together.
All kinds of.
What?
All kinds of.
What's that?
I'm asking you what you said.
I said this time we're going to flash LEDs that are connected together.
Connected together.
Yeah. So, and we're also going to learn a little about Ethernet. I think we should cover more of the Ethernet next time too, because it's quite involved, and I feel like there's probably a lot to learn for everyone. The difference in the LEDs is basically these microcontrollers are just turning things on and off in certain ways and order, and that's kind of what a lot of this stuff is. So LEDs are fun. The strip LEDs are especially fun. So we'll give everyone, I think we have enough for at least 4 for everyone to get. And we're gonna connect this to the Pico today. We also have an Ethernet NIC, which everyone have as well, and we'll use for the next time too. But basically, this is a Ethernet PHY, and we're going to connect the Pico to it, and we're going to send and receive Ethernet messages. Now, the tools and the software to connect it up to do that are kind of complicated. So that's why I think we're not going to, our goals should not be to necessarily get this working today, but you will have the code and you will have this board. So if you want to work on it to the next meetup, that would be awesome.
Are the LEDs individually addressable, or are they just like more of a standard LED?
I'll talk about it, but yes, they are individually addressable, which, like, I mean, that's probably one of the coolest things you could do with Pico is buy one of these on Amazon. I have a link for Amazon, so you could buy these for a lot of money or a little bit of money. Mm-hmm. On Amazon, you get them for a little bit of money, probably other places even lower. But I think this is like $16 for 16 feet. Then you add the Pico in for, $4. And you can do a lot cool. You can light up your TV or underneath your bed, to get in the mood. I don't know. So there's a lot of stuff you can do. But anyway, you learn how to control them. And what's really cool is that each individual pixel or LED can be its own 24-bit color, and you can do a lot of like cool yeah. And there's really no limit to the length you can do. So if you want to do one all the way home for your robot to follow you or something.
Yeah, the limits are how much power you can go, and it takes time to propagate the signaling through the chain. So
yes, yeah. So surprisingly a lot. So if you're down this holiday season, Christmas time, you should run these on your house. So.
Yeah, we did that at my old house.
You did, yeah.
Yeah, we have WLED software. And,
yeah, people make software so you can do it to music and stuff. Your neighbors will love it, especially if you put Clark quiz while your house.
And the great thing is you can do them up all year and then just change it for colors for every holiday.
Yes,
we did.
You're really good, yeah.
Red and green for Christmas, rainbow for Pride, and so on and so forth.
Yes, any holiday. Every holiday needs a color. So hopefully what the goal today is you will get these going. And I soldered mine. It was quite a bear to solder for me to do that. So hopefully you guys have better skills. Someone here has a technique. I was looking for like crimp connectors, make it easier, but I didn't see any. So everyone was like, it's so easy to solder. But I don't know whether it was my soldering or what. But what's also awesome about this, it's only 3 wires. So it's fairly easy to connect to the Pico. Now the Ethernet NIC is not really made well for the breadboards. It's got a dual row of pins, and there's actually there's 14 pins on here, but you have to connect 12 of them, I think. Yeah, I can't read the split screen, but it's a lot. So this over here, I have it connected and working-ish. All these wires have to be connected. What's good is that certain ones, if they're connected, it mostly works, so you can kind of debug it fairly easily. If it's not transmitting or it's not receiving, it's probably those wires. But what is interesting is there's a 50 megahertz clock that comes from this board that clocks the Pico, and I'm running over quite a bit of wire. Still, that's why I think it's mostly working, which I'll show you what that means.
So is there any way that the Pico could transfer to the lights wireless? Or does it have? to be
No, there's
connected to the
no
lights?
wireless
Oh,
connectivity built right on the Pico itself.
Yeah.
Yeah.
It's kind of a bare CPU with memory.
So I have to use maybe like a Raspberry Pi 4 or something?
No, we'll eventually get into wireless in this. So there's two things we're gonna do. I think first we're gonna start out with the 900 megahertz radio, and so what that will let you do is, that's just a specific band. There's no protocol like IP. So I don't know if it's gonna be simpler or harder, but it's definitely cooler. And the other one is Wi-Fi, which someone mentioned in the chat. Was that you or?
Yeah.
Yeah. Okay. So there are some microcontrollers that have Wi-Fi built in, and we'll use them as a peripheral to expose it, which is cooler than Ethernet.
Wait, make our own Wi-Fi?
What?
Make our own Wi-Fi?
Well, there's a chip, a peripheral chip that we can connect to the Pico to do Wi-Fi. Yeah. Well, like what I imagine is as this class progresses, we'll have quite a library of different options, and then maybe after the 10th meetup, we'll have one where everyone kind of builds their own project from the pieces. So like for example, last time we did infrared, so you could definitely after tonight, you could take the infrared thing that we built last time, which I have more boards if you want to hear that last time, but you can use that code to control the LEDs, for example. So on your TV, you take your remote. Here, there's a button you don't use. Use that to turn on the LEDs behind the TV or whatever, or underneath your bed. Turn it to red or something. Pulsing. Here I have a waveform up on the Pico scope, and I'm connected to the pin. So there's only one wire that goes to these LEDs, and the way it works is that there's just pulses that actually go through all the LEDs, and then they stop. And when they stop, they all get loaded in with the color. That's the basic idea. Now, how to do this with the Pico? There's different ways you can turn bits on and off with the Pico. One way is you can just do what we did in the first class, where we just GPIO, turn it on and off. And that works. It will work fine. The problem is that you use the entire CPU doing it. So usually you want to do other things. So for example, if you want to do the IR to LED, you'd want to do the RR, and you would want to do this at the same time. And that's kind of when the projects get really interesting. If you just want to do LEDs, you can usually use Python, but one of the benefits of C++ is it allows us to do many things at once with this small microcontroller. So we don't have to spend $50 on a Raspberry Pi 4 or something, which are very hard to get right now. So that's one way, and then another way to generate these pulses is through the PIO, and that's a major. It's more almost like a separate CPU on the Pico, and it actually is quite a differentiator in terms of other processors. And what it is it's this kind of an additional processor that's just made for turning bits on and off and moving data around. And that's what we're going to use for this class. There's another way to do it, and you can. I did it before without a PIO. Is that you can use a SPI bus to control these LEDs, and that allows you to use a peripheral on another microcontroller. So I had a Wi-Fi project where I made a scoreboard for my son's baseball team because no one ever knew what the score was, and basically the LED is made up to segments, and then that Wi-Fi microcontroller Wi-Fi, it was a TI CC 30 something. It would use a SPI peripheral to control the LEDs. But that's not why we're here today. We want to talk about PIO because PIO is pretty amazing. And, I'm going to bring up the data sheet. It's confusing because the Raspberry Pi Pico is the name for the single board computer. That's
Oh, you need the RP 2040 data sheet. don't
that's
you?
right. Yeah, yes. So RP 2040 is the chip. So if you dealt with Raspberry Pi for a while, they don't sell the chip normally separate, but this is kind of a different use case. So they do. So you can make your own boards with this part. The part is 70 cents if you buy direct from Raspberry Pi.
Now, the next question, is it available?
It's available.
Oh, my God.
Mainly because no one uses it. So it's kind of like once people
Well,
start
they're gonna
using it.
start using it now.
Yeah, so I think the lack of security is a serious limitation for using it in a product.
Oh, they just don't want people being able to dump firmware. There's no protection for that.
There's zero protection yet. So if you have any type of successful product, they'll just be copied instantaneously in China. But it could be used as a peripheral chip. So like if you have a security, you could load code in the RB 2040, like take advantage of the PIO, for example. That would be a use case for it, I think, a real one. But so anyway, interesting in the data sheet, the PIO gets its own chapter. So there's PIO, it's not just a peripheral, it's got its own chapter. So that's they obviously knew it was a big deal. Now there's no way you're gonna understand this now because it took me forever to understand it. But what it has is it has a 32 instructions it can run. So it's kind of like a mini CPU, and the instructions can control the I/O of the part, and they can also read and write to a FIFO or read and write to scratch registers. And it sounds very basic, but you can do a lot of interesting stuff with it. So first of all, the FIFOs allow you to send data from a CPU into this part. So that's kind of an essential part of moving data. So like you put data into it and then something happens to it, important. So like in our example with LEDs, we put kind of the colors of the LEDs, we push it into the part, into the PIO, and then the PIO program takes those bytes and turns them into this serial bit stream that the LED needs. Similarly, if you were going to write an Ethernet driver, if there's Ethernet messages coming on the frame, the PIO is going to take those bits and then put them into bytes, and then it's going to provide them to the CPU over the RX FIFO. So if you deep dive into the code, you will see that the PIO is used for both transmit and receive of the Ethernet and also LEDs. So what could be a real basic program? Now, if you worked in Intrepid, you know something about function blocks. This is like function blocks on hardware, which is really exciting when I saw it first time. Anyway, you basically have a sequence of steps, and every step is an instruction. There's 8 possible instructions. And they're very basic. So here's a basic one. It's going to generate a square wave. So when we did the IR LED, we used the PWM to generate the 40 kilohertz modulation frequency, and we used the PWM peripheral, and that's a very nice peripheral. It's fixed and it generates PWM, but you can also use the PIO to generate PWMs very easily, as shown. It sets the pin to output, and then it sets the pin high, and then the next one it sets the pin low, and then it jumps back to the start. So that very simple program is just toggling a pin, and this thing will run forever. As soon as you start it, it'll just run forever. So that would be an example of a program you could write. So you're kind of creating your own peripheral in software. So if you know anything what FPGA is, an FPGA is, who cares what it stands for, because it doesn't provide any insight what it does, but it's kind of software programmable hardware, and that's what this kind of is. Except it's very simple, which simple is nice because simple is 70 cents. You know, this part's 70 cents, not FPGAs. You know, we're talking dozens of dollars. You know, you can buy cheap ones, which are fun too, but it's a lot of complexity, a lot of learning. So what kind of instructions are there? Some of the basic ones. Jump, so that's jumping to a different part of your program. wait for an input or wait for something to happen. In will take stuff from the, actually will, yeah. In will put something into the CPU. So it takes it from a scratch register, for example, and pushes it into the FIFO so the CPU can rate it. Out is the exact opposite. That's what we use for the LEDs. We're going to take the bytes that we get from the CPU and put them in the scratch register so we can shift them out. Push and pull, those also, I believe, work with the FIFO. I don't know what those do yet. Move will actually move between different registers. IRQ is an interrupt, which we're not going to talk about. And then set will actually just set the pins. So let's look at a real program, one we're actually going to use today. So what's interesting about the PIO is you can actually do this LED control with 4 instructions, which tells me that when they designed this, they designed it with this in mind. It's very popular. It's very popular with the type of community Raspberry Pi normally targets. So it was very hard for me to understand this, but there's 4 instructions. There's an out instruction, there's a jump instruction, there's another jump instruction, and then there's a no op, which no op means don't do anything. And what makes this confusing is that and cool about the PIO is every PIO instruction can have a delay associated with it. So if you've ever did bit banging in a microprocessor, it's all about setting an IO and then creating a delay, setting an IO, creating a delay. But the genius behind the PIO is you can do them both with 1 instruction. So that's why 32 instruction doesn't sound like a lot, but you really can do a lot with them. Another thing they allow you to do is they allow you to control an IO pin on every instruction. And that's called side set. I don't know why it's called side set. You know, maybe because you can set it on the side of the instruction. That makes sense. So in this particular program, they use that feature to control the 1 wire. So even though there's an out instruction, a jump instruction, a jump, a no op, they're controlling the IO with this side set feature. So every instruction can have a delay, every instruction can control an IO, instead of just using the set instruction to control the IO. So it's very compact.
So you're almost getting like a pair. It's like a pair. It's able to do things in parallel.
Yeah.
Instruction.
It just seems so like perfectly designed for this.
Yeah.
It was designed for this, so that's why
Yeah.
it matches. I don't know, but my guess is they took a bunch of use cases and they designed the PIO around it. But I can kind of explain exactly what happens here. So this first instruction will pull a data byte from the FIFO that it received from the CPU. So the CPU is whatever, but I'll show you the code in a second. And it's gonna put the LED value, the color, into the FIFO of the PIO. This is going to read it. It's going to shift 1 bit out, 1 bit into the X scratch register right here. The second instruction is going to jump if the scratch register is not 0, which I don't understand that. But anyway, it's going to jump down to this do 0, and then it's going to continue. So it's just going to do a loop like that. Now, if the value is 1, it's going to fall down to this one, and it's going to set the pin to 1. So it starts out with 1. It looks at the value that it was shifted. If it's 1, it's going to set it to 1 on the side set, or set it to 0. So it's basically going to jump either to 1 or 0 based on whatever shifted out of X. Now this program does work. Let me kind of show you the code. So we're trying to develop a class library for this meetup, and so these are the 2 new classes. Okay, so let me show you the main code here. Okay, so I'm gonna just ignore all this stuff. We'll talk about that. So the class is instantiated here called, well, here's the include file, RP NeoPixel. And then here is the class. And this is the object. There's a init function called, which we'll just look at the code. But basically the init function will set up the PIO to control serial LEDs. That's the goal anyway. And the arguments are what pin? It only takes one pin, which is amazing. What PIO? There's actually two of them, 0 or 1. And then inside each PIO, there's 4 state machines. So technically, you could have 8 separate LED strips. Which, if you were doing a very huge project, maybe you could use it for that. But, and then what happens is we actually get this callback function from the Ethernet driver that said it received the Ethernet frame for the LEDs. And then we print it to the terminal, which is a USB terminal. And then we set the color of the LEDs from the data in that Ethernet frame. Then we call process, and that's what the process is going to do is it's going to push that data into the FIFO of the PIO. So coming to the implementation, this is a very bare bones implementation because, like I said, I got it working at 3:30 today, and I didn't use any example code for this because we were writing it from scratch, kind of. So I'm going to be using this for other stuff. But now, if you use the PIO with the standard way with the SDK, what you're going to do is you're going to actually use a PIO assembler. So they have an assembler, which is you write the instructions for PIO in a separate text file, and then you compile it along with your C code. And it's actually very interesting how they do it all, where you can actually provide the API in the same file in C. So they did a really nice job with that. What I wanted to do instead, because the PIO is so much simpler than a regular CPU, is just provide the compiler, create a compiler for the PIO inside the Pico itself. So you can dynamically generate a PIO program, which
I didn't know that. Oh, that's cool.
what?
I didn't know you could do that. I thought you always had to use the little PIO assembly.
Yeah, you don't. I don't know. Like Python has an implementation. MicroPython has an implementation of PIO, which I think they also do it too. So it's not terribly difficult to compile. And I'll have the code for the compilation as part of the project when I upload it in about a half hour. But basically this is that program: begin, wrap target, label, encode output, encode jump, wrap and end, and then start. So what this is, it exactly is this program. This program. So there's a wrap target, a label, the out instruction with the side set, the jump, another jump, and then an OOP. And then it goes and starts. So inside of here, there's another object we use called the PIO, which the PIO wraps basically a state machine in the PIO. It's not really just PIO. So it probably should be called PIO state machine. But going into that, there's an initialization function, which you pass in which PIO module, which state machine, what instruction, first instruction, and then the side set count. So if you're using multiple state machines, you might not use all the same instructions. You might have the first 3 instructions being one state machine, the next 5 for the other state machine. So you have to be able to set it. So what it's doing is now what happened was I ran out of time. So some of this stuff is specific to the WS LEDs. So this will be removed. But anyway, I had just copied the example to kind of get it working. But what it does is it initializes the GPIO pin. The way the PIO works, it can work on multiple pins, but there's a trick. They all have to be consecutive. So if you design a board, this is very important. if you want to put out 2 bits, those bits have to be, it has to be like bit 1 and then bit the next bit. And
So it has to be like a GPIO order.
yes.
Okay.
So that a common mistake designing boards around PIO is that, and I can give you an example. So the code that this is based off of the Ethernet is from this guy Sandeep, which is pretty cool. But if you look at the pinout, he has. So this is the pinout. So this is the module that we have, and then this is the Pico. Now, when you go your wiring, when you get to the wiring, which you can totally do tonight if you want, these are the wires. These are the GPIOs that you're connected to, not the pins. So don't. That was my first mistake. So just beware of that pitfall. But anyway, there should be another column here with pin. That would be cool. But if you see here TX1, it's got to be on any pin that's TX0 plus 1. Okay, because TX0 and 1 are it's 2 data bits that have to be together. So TX0 can be on any GPIO, but the next 2 pins, it actually rolls over. So I guess it could be on the last pin and then roll over. I don't know if you're feeling dangerous. So, and that goes for all the pins, output pins, the set pins, and then the side set. So this is amazing that this actually works. But this is just right from the data sheet. Now the WS LEDs, their bit is a pulse that's 800. That's basically 800 kilohertz. And the way it works is a 1 is basically the pulse is lower on one side versus the other side. So that's the difference between. Now we're going to show you. I'm going to show you the data sheet. But each pulse is 800 kilohertz. And so when we were talking earlier about how long could a LED strip go, it's based on 800 kilohertz. So you're 800 kilohertz per bit. So 24 bits for the LED. You know, I don't. Maybe a good assignment to figure out how long, 1 second update rate, how many LEDs you could have. So it's just simple math. So yeah, what is 800 kilohertz? We can just do it right now.
800 kilohertz is probably like something like about 1.25 microseconds.
Yes. All right. So how many seconds? Well, divide that by this one over 800.
Let's get you right back to 800,000.
Yeah, 800,000 bits per second.
All right.
Duh. So 800,000 divided by 24.
About 33,000.
Yeah. So if you wanted a 1 update rate, you could do 30,000. Now you need a lot of power. That's one drawback. I mean, you definitely power up externally. Each color takes 20 milliamps, up to 20 milliamps. So, you know, we're okay with 4 on this, maybe up to 8, 6 or 8. We're powering off the USB here, and
Yeah, that's about 2,000 amps to do all that.
yeah, 2,000 amps. So
At max. 33,333.
yeah, so you need a Tesla model, ludicrous or something. Okay, so anyway, this calculates the clock divider for 800 kilohertz, and what it comes down to is, I think, I'm actually not sure, but it comes down to the ratio of like 2, like these are a ratio of that. So these added together equal 800 megahertz, which I don't understand at all. But let's look at the data sheet of the LED. Wait, oh, there's one other part. So this is where the LEDs are set. So I'll show you that. So once this is running, that state machine is just sitting there waiting for data to come in that FIFO. Because what it does on that out X, it's trying to pull something from the FIFO into the shift register. And if it's not there, it's just going to sit there. So the CPU is going to set the LEDs, where that happens is we set the colors, and then here we call process. So we look at the LED class. The set color, pixel number RGB. I'm almost certain that these are in the wrong, or these are set in the wrong order based on my testing. I think it's GRB. But anyway, it figures out in this array. Okay, let me show you where that comes from. So here we have an array of pixels, and this holds the colors. It actually holds it in the class until we have time to process them. So what happens is the CPU is going to change the colors, and then at some point you're going to process them, which is kind of like when you do graphics drawing, you do all these graphics calls, and then you update the screen. So this is a list of colors, and the way it works is for every pixel, the first pixel is 0, 1, 2, 3. The second pixel is 4, 5, 6. So back to the set color. So the pixel number, and it's going to be multiplied by colors per pixel, which for this LED is 3. I guess they have LEDs with 4 colors. They have a white as well, because it's hard to get a nice white out of these. So anyway, we're doing 3 tonight. The second pixel would be 2 times 3, which would be 1 times 3, which would be 3. So this would be 3, 4, 5. So that basically sets that up in memory, and then process down here. What it's going to do, it's going to go through the entire array of pixels, and then it's going to build a word. Now the FIFO itself are 32-bit words, so that means it can hold each location in the FIFO can hold 1 pixel. So we combine all these.
24 for the color.
Yeah, so it's fixed at 32,
Okay.
and we only need 24, so we fill up 24, and then what you didn't see in the details is that you can configure how many of those bits you use in the FIFO, and that is this function right here. So this function outshift tells you how many pixels. But basically, this function, I have it set to 24. Now, if you look at the examples online for the NeoPixel, you'll see they'll say, do you have an RGB or a RGBW LED? And that will be set to 32 for the other type of pixel.
Wait, is that like an output? The W?
What?
No.
No, it's a white. So
Oh.
so with the LEDs, it's hard. Like the white is like,
Super blue.
yeah.
This is like you're thinking about a display or alpha where you want to have something where it can like let what might be behind in the Z ordering come through. LEDs don't. There's no such concept.
Right.
So
They
but
do
they
have
have a separate white. They have a separate white element as opposed to just having RGB LEDs. I mean, you can in theory make white from just the correct
From the other
combination of
three.
RGB, but
Yeah, you could try and make white tonight. That's what I say. I mean, make it snow. It's Michigan. It's May. Who cares? But yeah, you can see it gets. I don't know if it's white. I mean, it's white enough. I don't know. But like, there's white. There's like a natural white where it like looks good. Like
Warm white.
yeah, warm. Yeah, it's like
that's
you
part
could
of what
like
they're doing.
you could study under it. It's like good for your eyes or
Well,
whatever.
it's like I've had it in my kitchen, and if you use like the make it look white, it would just look weird.
Yeah, it's like it's more like a natural light. So
Yeah. I use those lights in the office.
okay, so that's where we're only filling in 24, and then it calls this right to transmit FIFO on the PIO, and that is down here. So there's a function put blocking, which I don't know why it doesn't say FIFO. That was hard to find, but it doesn't say FIFO. Now the blocking means if the FIFO is full, your code's just gonna stop till it empties. So you gotta be careful with that. So that's always nice when a embedded controller locks up. But you don't know why.
Well, in theory, the PIO is gonna be pulling these things out as fast as it can get to them, so,
Yes, in theory. So
yes.
yes.
But you're right, if this kind of stuff can cause all, if you're not careful, they have a version of that that's non-blocking.
I'm not sure, but you can check if it's full. So like if you wanted to make it not blocking, you check and see if
Yeah,
it's
it's
room,
full,
and if it's not,
yeah.
then you put it in there. So
All right, yeah, either way.
which if I was doing this for production, I would do that because.
Yeah,
So let's look at the data sheet for this amazing invention. If anyone ever says that Chinese people aren't smart, oh, come on. First of all, yeah. This is just a genius idea. I don't know where it came from, but. So anyway,
Never would I say that.
what?
When I said never would I say that they weren't so.
Yeah. I've been there many times. So we have an office there, 3 offices there. So
they probably sell this part by like the whole,
what's that?
this part is sold by the whole.
I'm sure. Yeah. Everyone loves LEDs. I mean, everyone. I mean,
This one,
I feel like I
everybody loves
started
LED.
electronics because of LEDs. I don't know.
I need that ship those stuff last year. The Evergreen was full of the WS-24s.
Oh, really? So were they not available then? Or?
Yeah.
Now some of the English isn't so great, but
It's actually entertaining to read sometimes.
yeah. I mean, I'd say like if anyone started their career now, they should learn Chinese just to be able to read data sheets. Because like everybody in Asia had to learn English to read like data sheets from TI, and like now everything is kind of
Yep.
So yeah, so this is kind of a schematic of a strip, and what happens is the data comes in on DN, and the data gets clocked, those pulses go straight through and continue. And then as soon as you stop the pulses, whatever has been shifted in that LED gets sucked into the actual driver for the colors.
I think it's a matter of like when the pulses stop. I mean, I think there's like a timeout after
Yeah,
X
yes.
number of
Yes.
microseconds or whatever that it considers. Oh, we're loading.
Yeah, so this is basically like a 0 is time high, followed by time low, and then it's exactly the opposite for 1. So this is what the PIO is generating. It's sequentially generating. It jumps to a different part of the program to do one of these or the other. And then as far as loading, this is basically each LED has a timeout. As soon as that time passes, then it just loads it in. So there's a shift operation, and you stop, and then it gets loaded in.
Yeah, it's pretty ingenious because it's stupidly simple.
And then here it shows you the timing. So after 50 microseconds, it will load the. So I guess let's see it for real. Unfortunately, I don't know how to use Windows 11 to turn off TCP/IP, so it's going to start pulsing. I'm going to go ahead and measure this with the cursors. Whoa, what's that? Why? Why? Honestly, why? Wow.
This Windows 11 thing is kind of scary.
Yeah, there's only one feature I wanted, and it's so Windows has WSL2, which is you can run Linux in it. Windows 11 allows you to use Linux GUIs.
Wow.
So it kind of lets you use GUIs so you can like Linux more, and then the features of Windows 11 annoy you to the point where you want to use Linux more. I don't know. It's marketing over there. Good marketing.
There's also virtual machines, or just run Linux. And run Windows on a virtual machine. There you go.
What do you does that?
All right, so I'm gonna set up a measurement at picoscope. This is another piece of software that I don't want an oscilloscope from 1970. I want something that's made for like pulses and, I don't know.
Doesn't have something where just like can automatically find, do an automatic measurement.
Yeah, I'm setting up automatic measurement for frequency. So I'm gonna do it through between the cursors, rulers. So it adds these at the bottom. You can see it's 800 kilohertz between these two peaks. We can measure this pulse. Seems kind of short to me. All right, so we got a 1 over here.
I think I got a little lost. What are you trying to measure?
I was just showing you that it was 800 kilohertz.
Okay.
Yeah, and I was just going to show you the different pulses. So I don't have a mouse because I didn't set it up yet, and I can't use USB because I have a USB oscilloscope, a USB Ethernet NIC,
You need a USB hub.
and a USB. I need a hub, yeah.
I run into that problem all the time. The 2 USB ports per computer, if you're lucky, you get 3.
All right, so here's the opposite pulse, which is obviously 1, and it's also 800 kilohertz. It's just inverted.
Yeah, the duty cycle changes. The on time is different between if it's a 1 or a 0.
Now we have these oscilloscopes, so if you get it working, feel free to install Picoscope and try to get it working, or look at the waveform. All right, so this is basically the FIFO got loaded, and then how many bits came out? There's 4 pixels. Does anyone know? How many bits are here? There's 4 pixels. So 96 bits. It's a rough measurement of the update rate. So 120 microseconds to update the 4 pixels. And what's great is like the CPU just puts the data in the FIFO and continues to operate. So it can do things like process Ethernet. All right, so I'm going to do a quick overview of the Ethernet, and the goal is going to be to get the LEDs working tonight. So the first thing we'll do after this is you'll have to solder wires to the LED and then get it wired into your breadboard. Get the tools installed, and then I'll provide a download link so you can download the code. Yes. Yes, which I will probably delete once because the code is extremely embarrassing, but most of it's not mine. But I'll give him credit for it. The guy who wrote it.
The data in the event.
Yes.
Okay.
Yeah, I'll put it in the event. Okay, so what he's done is he actually took a IP stack, which is a set of software to do internet protocols called LWIP. And it's been around forever, and it's very stable, and everyone uses it. And it's open source. So that's actually going to be downloaded with this project. But it's not simple to learn, and we don't really need it for this class. Ideally, it would have just worked. So what happens when this starts up, it does do a DHCP request, which is a request for IP address to the PC. But for some reason, my computer is not responding to it.
Well, because if it's going to send out a DHCP request, it needs a DHCP server on the other side to give it an IP address.
That's why it's not working. Because I don't have one on my desktop.
Okay.
So if I plugged it into my home network, it might have worked.
Yeah. Do they have an option to just like give it a static IP?
Yeah, sure. I'm sure it does. Yeah.
Because that way you can configure the interface, your interface for static IP that would be within the same subnet.
Yes. So that's a whole other learning topic, is learning IP, which everyone should learn IP. No doubt about it, because it's everywhere. It's everything. It's in the cars. You're in
It's
the
in cars now.
Yeah.
Oh my gosh.
So anyway, moving along, there's a configuration structure for the Ethernet. Now, the Ethernet PHY, there's a standard interface to Ethernet PHYs. The original one is called MII, Media Independent Interface. And the idea is that the PHY is really the media, and it's dependent on the technology, where MMI is independent. It's just a digital interface to the PHY. So that's the original concept. Now the MMI, it uses a lot of pins. So it's kind of problematic on little microcontrollers or systems. So they came up with something called RMII, and it uses a lot less pins than MMI. So I think more than half. But you can see, even with RMI, we still have a lot of wires to wire to. This particular board is using RMI. It's a little bit more challenging because it's higher speed. So one of the things they do, it's also synchronous, which means that the clock of the output data is clocked from the PHY. So he developed this. I don't know why, probably because it was difficult to catch edges. He actually uses the clock for the PHY, the 50 megahertz clock, as the clock of the Pico. So that's what this line right here is. What's really interesting is on the Pico, could be a potential gotcha, is that the Pico will accept an external clock, but only from 2 different pins on the part. So if you're designing a part where you want to do that, you have to be careful about what pins you pick. So I was working on that, and I discovered that. But you can see he picks pin 20. So he calls in to some initialization for LWIP, and then there's these functions with the net interface. I believe, I don't know LWIP myself, but I believe that NIF functions are the implementation for actual interfacing with the actual hardware of your LWIP. Marty is nodding yes, so okay. So what happens is it does DHCP, so we need a server for that. And then it basically enters this tight loop. So it never really makes it down here. He had this multi-core launch where he was running it on a separate core, which I thought was cool, but I just didn't want to have any more complexity than necessary, because I have callbacks from the Ethernet driver to set the LEDs, which there's a right way to do that. I wasn't doing it. It could have worked. I don't know. So I just didn't want to mess with multi-core. So let's look at this file. Another thing to mention, and that's on his sheet or his GitHub. Is that his link speed is set at 10 megabits. So there was an issue with transmit 100 megabits. I don't know what the issue was. He's actually, I've actually interacted with him, so he was responsive. So if anyone does figure it out, I'd love to tell him. So as far as I know, it wouldn't auto negotiate with hunt down to a 10. So I had to go into my NIC settings and change it to 10. I don't know if that's necessary or not. So if anyone experiences something different, I'd love to hear it. So it's important to know. So I put a link into the USB to Ethernet converter I'm using. So I don't know if every Ethernet has that ability to set the speed. Seems useful. Although who uses 10 megabits anymore? I don't know. But so let's look at the. So this is the driver. So he wrote this and made it work with the PIO. So there's actually 2 PIO programs. They're surprisingly simple. So if you look at this PIO program, it's one instruction for Ethernet. So all it's doing is it's taking what's in the FIFO, taking 3 bits out of the FIFO and putting it on the transmit pins. So the transmit interface back to this is TX0, TX1, and TXEN. And of course, that clock is synchronous with the PHY because it's actually generating it from the PHY's clock. So it's pretty ingenious. The PIO program for RX is similarly simple. So it's a bunch of wait instructions, which I honestly do not understand RMII yet. I want to understand it, so maybe at the next class I'll be able to explain it. But he's waiting on certain pins in a sequence, and then he moves the value of the pins into the FIFO. So the in function, the pins, he moves 2 bits from that interface into the FIFO. Which, if we look at the hardware for the receive, we have RX0 and RX1. There's a function to calculate the CRC of a Ethernet frame. Ethernet frame has a 32-bit CRC. And the part where I kind of hacked here is RX frame. If you receive it, he had some things commented out to print out the RX frame, which I needed to debug. But the way I did it is if the frame was a certain length, I just called the callback of the LED message received. So I didn't use any of the stack or like the IP. I was just going to hard code like a UDP frame, which I didn't do any type of filtering on the frames. Any frame that was long enough gets sent to the LEDs.
It's not even UDP. These are just raw Ethernet frames.
Yeah, you can treat UDP as a raw Ethernet frame because it's connectionless. So it's basically you can generate a UDP frame.
Right. You just have to put the UDP header in there and all that.
Yeah. So this software, this packet builder. It's not on the screen. Well, there's an invisible app that you can't see called Packet Builder. I put the link in the Meetup, but oh, yeah, here it is. Okay. Yeah, it's kind of lagged. That's good to know. But anyway, this lets you build a generic frame. Yeah. Also, Vehicle Spy will, if you have a copy of that. It's expensive. That's the software we sell here. But this is pretty nice. It will send the frame too. So you pick the adapter, which I was using the NIC, and then send. And if I can turn off the TCP, which I'll figure out how to do tonight, you can set these bytes down here. It looks like they have some issues with DPI. But you can set the bytes down here and you can control the LEDs with this app. Other things to mention, so a key part of the Ethernet interface is the setup interface, MDIO. So there's this 2-bit or two line communication with the PHY. The PHY itself has registers where you can read and write them, and that's how you configure the PHY for different things. So in the code, there are functions which I have not looked at that's the first thing you do with the PHY is you configure it. So how he set it up to go in 10 megabit mode, that's in the code that interfaces to this MDIO. And we'll go over this a lot more next time. Now he originally planned to do MDIO with the PIO, but he didn't get to it. He just bit banged it. Really, you can do that because usually you're only interfacing with the 5 settings at the beginning. You know, some of the PHYs have like statistics about what's going on, which could be important to your application, like an automotive. That's a big use case. But in this case, no. All right, so I'm going to give you the code. You get started. We'll talk more about the Ethernet next time, and I'll probably have better code next time. We'll eventually make this wireless if that's what everyone wants. Although Ethernet, you could power it off of Ethernet too, so that's kind of nice. But I don't know how many LEDs you can power off of PoE. So PoE is kind of a nice feature of Ethernet. What's that?
Like all my access points in the house run off of
Yes. Yeah.
They take a decent amount of power, so.
Yeah, I think you can do 15 watts. That's, you know, it's probably enough for like a front porch or.
Yeah.
Like there are some new people here. Can you tell a little bit about like where to find the beginning of Raspberry Pi stuff?
Yeah, so if you missed the first, everything's in the first meetup, which I probably forgot all of it already, so I'm gonna go back to it. Yeah, we had a whole class installing the tools. This is so much work. Really is. But Marty, where Marty went, he's did it at least 15 times already, so he probably could do it without, he's like a wizard, right? Okay, so our events, past events, 105 members. Where are they all? Slackers. All right, come on, you can do it. Okay, so we followed these instructions by Sean Heimel. He's kind of a YouTuber, famous for embedded stuff. Works a lot with DigiKey. So that's this link right here. And we basically followed it step by step. Look at it. So we kind of did step by step for Windows, but you can obviously install it on the Mac. We did get MacBooks up and running in the first class. So, oh, there's one thing I did not show. The project has a USB interface console to the PC over a COM port. We're going to cover USB at some point, but Pico does a really great job with this, making it so easy. So printf just goes right to the USB port. And you can see there's a COM3 here. So if we go to COM3, the speed doesn't matter. So let's callbacks plugged in or plugged up. Well, it seems to be working better than it did at my house. Oh, no, see, the link status goes down and up for some reason. I don't know why it does that. I don't think it's supposed to do that. But anyway, this is kind of a useful debugging tool where you can print off from your code to see what's going on.